Today's video is going to be the second part and the concluding part of the repair on the Fnirsi IPS3608. If you haven't already watched the first part, I recommend that you watch that first, because the second part is a little bit meaningless unless you watch the first part first. So if you'd like to see a video concluding the attempted repair of the Fnirsi IPS3608, then this is the video for you. So let's go. Okay, so I'll just start by popping a couple of these into the TC1 and see if the parameters are quite similar. So we've got a gate threshold of 3.35 and the RDS of 0.2, which is the same. That one's got a gate threshold of 3.37, RDS of 0.2. I'll try and get two that are matched as best as possible. 3.36. 3.35. Okay, so those two are 3.35. And let's just check those on the peak. And our MOSFET. So that one is saying 3.25. If this one says 3.25 also, I will be happy. Had a short circuit on the legs, I think there. Try that again. Yeah. 3.24, I think that's close enough. Okay, so I'm going to install these two MOSFETs. So let's go ahead and do that. We need to bend the center pin. The board, I suppose, before I do that. So, two screws. Right, so the insulator is still on the board for that one. Okay, I think that's in. So we need the other insulator, which I seem to have lost. Where did I put that? I don't know. Okay, I'll just have to find that. She'll be back in a moment. Okay, got it. Slightly, it's a new one. I've got a new one. Right, okay, solder those in. Leave the heat on these for a long time to enable the solder to flow all the way through. Got the solder line set to 350 with leaded solder. Okay, I think that'll do. Let's snip the legs off. And clean the board. Yep, that should work. Okay. Now I can reassemble. So again, I don't really need to do these up super tight, just give them a little bit of torque, nothing severe. Good. Right, put the ribbon cable back in. Again, to make sure that that's in evenly in the right spot before closing the clamp, like that. Okay, next let's get the main unit back, and we'll start by reconnecting the USB power. So the ground is at the edge. And again, I'm actually applying a decent amount of torque to these terminals. They do have quite a lot of current going through them, especially these ones. Put the plug in. Right. Okay. I'm just going to pop the front back on loosely, and we'll put the knob on. Okay, so let's see what happens. Turn the switch off, put the power in. I'll angle this guy up like that. And here we go, power on. Wow, okay. So far so good. So let's just do a quick test. So I'm going to set the voltage. I've forgotten how to operate this thing already. There we go, right, set the voltage for 1 volt. And 100 milliamps. So let's press the run button. Does it go green? No. Okay, so it's flickering on and off between run and stop. That's not good. Five volts. Okay, 5 volts 1 amp seems to work. Okay, let me let's just check the voltage coming out. Okay, so we set for 1 volt and we've got 1 volt. Two, 3, 4, 5, 6, 7, 8, 9, 10. Let's go 20, 25, 30, 31, and the maximum 36. So that all seems to be quite good. Okay. Right. So we've got a current limit. Let's turn the voltage down. Okay, so we've got 5 volts 1 amp set. Okay, 1 amp. Let's get the meter in. DC amps. Right, we're just running straight through the meter. Output on. Okay, so let's set for 1 amp. We've got 0.992. Two amps, 5 amps, 8 amps, 8.2. That's maximum. That's good. Okay. Let's go down to 10 milliamps. Fan has just kicked in, 33 degrees. Yeah, so it actually seems to be behaving itself. I don't know why the initial output refused to switch on correctly, but it seems to have resolved itself now. Okay, I'm going to get my load out, well actually put it on load and see what happens there. So I'm just going to set up for that. So I'm going to go ahead and do a factory reset just to see if that might help with anything. Yeah, so what the problem I've got is that the voltage is just flickering around. So with no load on, I've actually got some voltage flicker going on here. Have I actually got anything at the output? I don't know. Let's have a look. Yeah, so I have actually got some output. I would imagine it's because those MOSFETs aren't the genuine ones, and they may be leaking a little bit or something like that. But it is quite encouraging. The thing is actually working. So let's just load this up. I just want to see what happens under load. So I'm going to do the load test that caused it to overheat. So that was 18 volts at maximum current, and we'll turn that on. Okay, 145 watts. So let's just see how quickly that heats up. Okay, so it's gone over temperature protection. Similar kind of time. So I don't think there's any real change there. And again, it says it's running, but there's not actually any output. That's because my load overloaded. Okay, so it didn't actually crash. I think it cooled down considerably quicker than before, potentially. Right, okay. So we're definitely getting a bit of voltage creep going on here. Right, I'm just going to have a look to see if I can see why that might be happening. Okay, so it seems like I've got a capacitor here which is not very happy. It's measuring 230 ohms, so I'm just going to take that out. Doesn't look happy at all underneath. It's very black, but it is actually measuring 200 nanofarad. Okay, so this is the capacitor under a microscope. Now this is the bottom of the capacitor where it is actually soldered onto the board, and it doesn't really come over very well with the contrast of the microscope, but the underside of the capacitor was black. It was literally carbonated, and it obviously had been flashing over in some way, causing this issue to occur. Now, whether that's contamination from assembly or manufacturer, I really don't know. But I'll just turn the capacitor over and we can see the top side. So this is an 0603 capacitor. Okay, so that's one of the other sides. I don't know if that's the top side or one of the sides, but you can see that it looks kind of normal compared to the bottom. And there's the capacitor itself in normal lighting conditions. You can see that the underside of the capacitor is very black, and the top side is kind of normal looking. So what I'm going to do now, I've measured the capacitance of this. That didn't look to be too bad. But what I'm going to do now is I'm just going to test this for leakage. So I'm going to use just a really basic little leakage tester and see if we can see any major leakage from this thing. Okay, I'm zoomed in quite a bit here so you can actually see the capacitor in there and try and see me testing it. So this guy here is a homemade leakage tester, only works at low voltages and goes up to 1 milliamp of leakage. Now I'd expect a multi-layer ceramic capacitor to have an extremely low leakage current, very low, you know, in the tens of microamps I would guess. I don't actually know, but you know, that's the kind of thing that I'll be looking for. So let's see what this guy does. So I've got, this is what's known as the approximeter. It's a homemade 1 milliamp full scale ammeter. So let's put the probes on this guy. Yeah, so we've got way, yeah, you know, that's way over 100 microamps. If I make a really powerful contact, you know, that's going up to over 250 microamps. Now in my opinion, that's way too high for this type of capacitor, and I think that that is the failure mode. So this capacitor has gone for quite leaky. So let's measure that now. Just can I get that in? Probably. So it's measuring 200 nanofarads, and ESR is a little bit variable at 10 kilohertz, about 5 ohms. Now obviously this is going to operate at quite high frequencies, I would imagine. Let's just put it onto 1K frequency. So the capacitance is near enough the same. ESR is about 15 ohms. Now that's obviously with Fnirsi. I know some people prefer the Zoe, so let's do the same test with the Zoe. Let's put it on to 1K and capacitance mode. Yeah, see, personally I prefer the Fnirsi. Let's do this with the Zoe. So the Zoe is measuring it as 213 nanofarads and about 15 ohms ESR. Let's just put it onto 1K. Sorry, onto 10K. 10K, here we go, eventually. So we've got 206 nanofarad and the ESR is 1.6 at that frequency. And of course, if you'd like to see a video where I build and give the circuit diagram for the leakage tester, I will leave a link in the description for this video, a link for the video where I show you how to build this and the circuit diagram. Let's just leave that off and see what happens. Yeah, so I'm not getting my output voltage drift now, but that has killed the unit. Has it blown the fuse? Yeah, so the fuse is blown without that cap in there. The MOSFETs don't appear to be short. Yeah, the fuse is definitely open circuit. Right, so I'm going to put another cap in there because that might be breaking down. Let's see what I've got. Okay, I've got a 220 nanofarad. Just test that. That measures 184. I think that's close enough. So let's pop that in. Okay. Just see where that's going. So that's kind of going to the source of the transistor via a small value resistor. Another fuse. Okay. Okay, well, I haven't got any output. And that capacitor is cold. So the capacitor in question, the one that I actually changed, is this guy here. You can probably see that's been changed. It's not quite dead straight, but anyway. So this IC here is the driver IC for the two MOSFETs. Now there's a high side and a low side MOSFET here, and these appear to be connected to the positive side of the power supply. You've also got a couple of MOSFETs down here, which are connected via the 15 amp fuse to the negative side of the power supply. I think that's the case. Let me just quickly check that. So we're in diode mode. So the positive side, so if I go, yeah, so we go to this guy here, so the positive side is connected to that, and I think the negative side, yeah, so yeah, so and the negative side is connected to these two MOSFETs here, which then goes through the 15 amp fuse. So this will be the output of the MOSFET to the 15 amp fuse here, and then to the negative terminal. So the positive side actually has a 10 amp fuse and the negative side has a 15 amp fuse. Why they've done that, I'm not really sure. But what I will say is that actually these fuse holders are only ever rated to a maximum of 10 amps. I've looked at the specifications for this type of fuse holder, particularly from the original manufacturer, which I believe was Little Fuse, and these fuse holders are only actually rated at a maximum of 10 amps. So putting a 15 amp fuse in one of these fuse holders is again something that Fnirsi have taken upon themselves to do, and is outside of the specifications of this fuse holder. So then if we come to the purpose of this capacitor, so what we saw in the video is that without the capacitor in there, and the good MOSFETs, no capacitor, good fuse, the fuse is blown instantly. So that's effectively somehow creating a short circuit across that fuse by not having the capacitor in there. So this chip, we'll look at the data sheet for this chip. The chip itself is an IPS3608S, I believe. This is the closest data sheet that I could find. So it's a half bridge driver designed to drive high and low side MOSFETs. We've got a basic schematic here. So we've got the low side and the high side MOSFETs. So the capacitor in question is this guy here. So it's actually, this is kind of like a bootstrap circuit, so it uses the diode, the capacitor to get these things to transition from high to low. And with this capacitor out of circuit, probably both MOSFETs turn on at the same time, creating a short circuit between ground and the supply voltage, thus blowing the fuse. So this capacitor is very, very, very important. Okay, let me just put the front back on. Okay. So I haven't got the output drift now that I had. actually forgotten how to operate this thing. So we set the current limit 100 milliamps, 100 milliamps, voltage, God. 5 volts, output on. So let's check the output voltage, DC volts. Okay, so the output voltage is on. Let's turn it off. And so if it goes to 0, it does. Okay, so maybe that capacitor failed. It does seem to be behaving itself now. Okay, I'm just going to leave it on for a bit. And have a bit of a tidy up. And let's just put a bit of load on. Uh, 5 volts, let's just go with 1 amp. Or 5 volts, 1 amp. Okay. The output off. Disconnect power, so it is remaining at 0 volts, which is good. Let's just turn off. And I've just turned the load off, so I'm going to start it up with no load because we've kind of proved that it doesn't really like that overly. Okay, so far so good. So I'm going to turn the load back on. So I've got the load actually set for constant current 8 amps. So whatever I set on this is it's gonna do basically. Okay, let me increase the voltage here. Let's go 25 volts and keep it at 1 amp. I had to reduce the current on my electronic load because it had an input voltage of 25 volts and I had it set for 8 amps, so that was calculating that has been an overload situation even though it wasn't actually receiving that. Right, let's increase the current. Okay, let's just turn it off. Yeah, so the output voltage has dropped down to 0, which is good. Okay, let's put that back on. Let me reduce the voltage. (18 volts). I can increase the current on my load. And now we can slowly increase the current on the output, so it's got up to 7 amps. Come on, we should be going back into constant voltage. Which it's not. Over current protection. So it has decided to go into constant voltage mode now. I don't know why. It didn't do that earlier. So all is not 100% brilliant. Anyway, so I've got 18 volts, 8 amps, which is kind of my default test at the moment. So I'm going to leave it on that for a while until it shuts down. So let's just let it cool a couple of degrees, and then I will re-enable it and see if it starts without any crashes, and then I will turn the output off again to make sure it goes down to 0 volts. So it does seem to be cooling down quicker than it did previously, I have to say. Maybe the ambient temperature is a bit cooler than it was. Yeah, I think the ambient's a bit cooler, but not a huge amount. It's 20.2 degrees in the workshop at the moment. Okay, let's get the output on. Yeah, and that seems to work. Okay, now I just want to drop the current down. Okay, so I've got my electronic load set for 8.08 amps. Now I'm just going to reduce that down actually to 8. Okay, so I've got it set to 8.0 amps. So let me slowly increase this. So that should really be going back into constant voltage mode now, but it doesn't seem to want to. Only if I turn it off and back on again. I'm not sure if it did that before, I really don't know. Okay, so I'm just going to go maximum voltage. My current limit set for 3 amps on the electronic load, which it is doing. Now I personally wouldn't expect the temperature to rise as fast because I'm not dropping as many volts across the MOSFETs, and therefore the internal resistance, although very low, is going to have less of an impact. So let's just leave that running. Let's actually get that up to 100 and there we go, 145. So we've got the equivalent wattage, but double the voltage, so half the current. Let's just see what happens to the temperature real quick. Yeah, it's not changing, so it's happy delivering 145 or 143 watts at maximum voltage, and the temperature instability really comes in when you start dropping the voltage down, and that will be because of the internal resistance of the MOSFETs. So it would appear as if I've actually managed to repair the Fnirsi IPS3608. At the moment it seems to be behaving itself. I do need to see if it switches out of constant current into constant voltage and vice versa on the fly. Maybe I'll check back on the original video and see if I can actually see that. But it appears to be behaving itself. So I hope you enjoyed this video. If you did enjoy this video, then please give the video a thumbs up and consider subscribing to the channel if you like this kind of content. There is a whole load of videos on this power supply that I seem to have now, so please check those out. Yeah, so having said that, I hope you enjoyed this video and I will see you in the next one.